good. Yeah, okay. Cool, this is working. I just don't see my chat up on my screen. Why is that? That's annoying. Come on, girl. Yeah, we're already signed in. YouTube's been changing a lot of stuff recently. What's up, Iz? What's up, Asta? Thanks. Yeah, I'm just fixing my chat client so that I can see the chats you guys bring in. I have it on like a separate window, but I have a nice little prompter that makes it easy if it wants to work today. I'm just gonna call this social stream. Three beatings? Sensation. No, homework 1 is not worth 3 beatings. Oh, they really, wow, oh, they really changed social stream. Oh, man. Ooh. Oh, yeah, they totally changed this. Okay, yes. Allow access, whatever, just, let's firewall stuff. Allow. Yes, great, cool. Okay, very cool. I can see that chat. There we go. Okay, now my chat's working. Nice. Good job. Sorry, had to get that fixed. We changed a lot of things today. This, I mean, it's the world of just online stuff. They're always creating updates. And you have to like constantly like replace things with new versions, and then they break things. And, yeah. And now I want to like remove this one, but I want to pin this one. Okay, cool, awesome. Okay, I think it's all working. It's more scared now. Don't be scared. Yeah. I mean, what does it say in our syllabus? What's homework worth? I don't remember everything. I remember it's higher than I used to have it because this is an online class. And, you know, I can't exactly get you guys in person to take tests, so I have to readjust for the one thing that is a good indicator of how much you care about this class, which is being responsible and doing your homework on time. But let me see. I think it's 20% is the whole thing, right? We'll start lesson here real quick. Just give people a couple more minutes to roll on in. Hope you guys are having a fun Thursday. What's up, Cameron? Okay, yeah. Let's see the. Let's see what does the syllabus say? Syllabus says. Oh, also I need to update this. I need to put in what we've done so far. Okay. Homework is 20%. Okay, cool. And then how many homeworks are there? Well, that's a good question. So, let me check on Kudu. How many homeworks well, I can actually already tell, right? So we have 2 homeworks from here, 2 homeworks from here, that's 4. 2 homeworks from here, that's 6. 2 homeworks from here, that's 8. And then I forget if there's 2 sections in Kudu for the last one. Let me check real quick for you guys. Is our last week really all... It's not going to be entirely review. I just put that as like a buffer. We may go and... I may need more time for the topics. And then, you know... Yeah, because like 5 days of review, like what? Just sit here and do physics problems all day, I guess. That's just what most professors do. Most professors, they reserve that last week as review, and then it becomes like a buffer if you have to like spill over more teaching periods to do things. All right, let's see. One sec. All right, we've had 1, 2, 3, 4, 5, 6. You've had 6 homeworks so far. 7, 8, 9, 10. 10 homeworks. Okay, cool. So here, you guys want to see how like the math works for that? Because people do ask this. They're like, oh, what happens if I miss a homework? Well, don't do that first. So 20% of your grade is homework. Okay. And so that's like 20 points, right, out of 100. And then if there are 10 homeworks, right, that means each one is 2 points. Okay. So if you completely miss a homework, which I recommend not doing, you lose 2 points on your total grade. So you go from 100 to a 98. Like, oh no. It's not that bad to lose a homework. I mean, if you lose a couple homeworks, it starts getting bad, because then it's impossible for you to get to certain grade levels, right? So yeah, each homework is 2 points. All right, let me read real quick through the chat, and then we're going to go into more of Gauss's law. Okay. Should we be worried if we're falling behind on most recent readings, like maybe last 1 or 2 chapters related to electricity? No, not too much. I understand that you're probably prepping for the test tomorrow, and it's hard to do that while we're also learning new things, but that's just the schedule of what we got to do. So try to use this weekend to really catch up. So once you do the test on Friday, you know, we don't have lecture on Friday, so you don't have to do anything on Friday except the test. Try to use like Saturday and Sunday to catch up, because yeah, summer courses are fast. If you start falling behind, it's very hard to catch up. So yeah, try to do that. Some of your UCLA profs straight up taught to the very last day before exam week. Well, that's kind of mean. I wouldn't be introducing new material like the day before exam week. That sucks. Like what? Too much math. Yes. Yeah, so quick announcements. Tests will be available 12:30 tomorrow. Here, let me turn the music down. So, lo-fi hip-hop's loud. Okay, sorry. 12:30 tomorrow. Yeah, I just met with the TA, Albert. Lovely guy. He gave a lot of really good feedback on the exam. He wanted to like clarify some things, give you guys some more hints. I'm like, cool, awesome. You think it's fair? We'll do it. So I got to go edit the test with his suggestions today, and then it'll be released tomorrow, 12:30 p.m. I'll put this on an announcement later, but for those that are watching right now, good job, you know.
Nice.
But yeah, 12:30 p.m. and then you need to have the Kudu section will close at midnight. So you have to have your answers selected or like inputted in before midnight. Like, please check that it says like saved and whatnot as a backup, because I know, believe me, I get so many emails every day about like Kudu didn't do this, Kudu didn't do this. As a backup, you're also going to submit your work on Gradescope. There will be an assignment. Albert's setting that up, and you will, like, pen and paper, also put what your answer choices were on Gradescope. That's a backup in case I get some woe is me, like Kudu didn't save anything, I get a 0 on the exam. Make sure you've uploaded some paper to Gradescope, because if I see that, then we can give you credit for things. Albert is cooking. He's great. So yeah. Yeah, not really scratch paper per se, because I want you to show your work. It's not like don't just show me a bunch of fucking mess. Like, yeah, no. The thing you turn into Gradescope should be like organized. It should say like question 1, here's my answer, and then maybe quick little things about like how you got it, you know. If it's some multiple choice question where it's like, you know, yes or no, or it's an easy, you know, you don't have to really write that much. But if you did like calculations, like show those, please. Yeah. Format. So I changed the format exam. I'm making it shorter, just to be nice. Cause yeah, Albert was right. He's like, it's a little bit long. I'm like, yeah, 12 multiple choice and 3 free response. It's like, it's a little bit too much for a midterm. I mean, on a final, it's totally fair game. But so I condensed it down to 2 multi-part free response questions, and then there's like 8 shorter questions. 4 of those are strictly multiple choice. 4 of those are like numerical, put in a number. So you have like 8 not so difficult questions to solve, and then you have like 2 longer multi-part questions to solve. And yeah, with Kudu, you don't get any checks. You don't get any like check answers. You don't get to just like start guessing and like trying to mash it to figure out what the answer is. So you just put your answer in, what it is. I hope Kudu records it. If it doesn't, please, again, sheet of paper, upload to Gradescope, box what your answer choice is for each number, and we'll make sure it works. There's no real time limit on the exam for this one, because it's the first one, and I know people are getting used to things. I mean, people still aren't figuring out how the homework works. I'm like confused, but it's okay. Kudu will not tell you whether it's correct or not. No, because there is no check answer. I'm going to disable check answer, so you don't get to know whether you're right or not. You'll know whether you're right or not once it closes at midnight. Which, now that I think about that, I know I'm going to have some kids with some emergencies that like can't do things. Whatever. I'll figure it out. I got to figure out the technology of this, but just get it done by midnight. You know, that's the time limit. You get almost like a full 12 hours. It shouldn't take you more than an hour, maybe an hour and a half. But I'm trying to be as accommodating as I can for all of the international traveling students who signed up for this course. Which I get. It's an online course. That's probably how they market it. I don't know. UCLA just asked me to teach. I'm finding out now that like, oh, this is like supposed to be asynchronous, blah, 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 blah. But I have to like put some sort of restrictions. Otherwise, it just becomes like everyone gets an A. And then the department gets mad at me. So my hands are like tied. What am I supposed to do here? So anyways, yeah, don't worry. It's only 10% of your grade. You'll know your grade probably by Monday, I would hope, if I figure out how all the grading stuff works. Don't worry. The Kudu points assigned is not accurate to what the rubric's going to be. I'm gonna weight, you know, things differently. And I'll announce what that is afterwards. I still got to figure out how I'm going to get Kudu points into... I think I'm going to go into Gradescope and manually assign things. Yeah, you get an A, you get an A, everyone gets an A. Yeah. Just do your best. That's why I say don't worry too much about, like, you know... Let me figure out the logistics of what all the point assignment stuff is, and you just focus on learning physics and understanding things and doing well, and you'll be okay. Okay, sorry, that's enough time for me ranting things. If you have any questions, yeah, please, you can always send, like, I love what you guys are doing on Campus Wire. Just dump stuff on Campus Wire. I'll answer it. And I'll make an announcement later tonight about, like, full exam details. Okay, cool. All right, let's start off. So, yes, and I'll tell about the partial credit afterwards. Yeah. after you take the exam. But just make sure you write on that paper what you did, because that's how you get partial credit later. I mean, this is also the first exam, so we're going to be, kind of figuring this out together, the logistics of it. I think it's pretty new for UCLA. I don't think UCLA has really done this before, like summer physics classes. Okay, so yesterday we did Gauss's law, right? Which told us that electric flux, which is equal to the integral of E dot dA, surface integral, is equal to Q enclosed over epsilon naught. Okay. Now, something that came up was really interesting in the chat yesterday is someone was asking, hey, what about the electric field in a conductor? Right? And it turns out the electric field in a conductor is equal to 0. And we can kind of like explain why that is. So, let's say, for instance, you have a well, let's see. They showed like the charged ball here. I guess this is kind of cool. Yeah, whatever. Let's use this picture. Okay. Well, I'll use it in a bit. Okay. So if you have, for instance, a non-conductor, right? Like an insulator or whatnot, but it has charge on it. Okay. And actually, let's use brown for this. Like wood. This wood is very good, like insulator, or like non-conductor. Okay. We know that insulators or non-conductors do not allow electric charges to really move around much. Okay. So if, for instance, you had something that was positively charged but was an insulator, okay, you could expect that if the charge was uniformly distributed, right, it might look something, I'm trying to make it as uniform as, it might look something like this, right? So the charges are, kind of evenly spaced within your material, and they're not moving. Okay, that's an insulator. It's very easy to figure out the electric fields, and we'll do an example of this, finding the electric fields, because if you were to draw any sort of Gaussian surface, like any sort of, right, sphere or whatnot inside of it, you would be enclosing charge, right? And if you're enclosing charge, then you must have electric field. So in this case, E is not equal to 0. And I'll go through an example of how that would work with a sphere, because the electric field actually changes as you get further and further from the center of it. Okay. If you have something like a conductor, though, okay, let's use like a shiny color. Let's say like, here we go, silver ball, or here, let me make it like, yeah, there we go, silver ball. Okay. Let's say this, for instance, this is a conductor. Okay. In this case, charges are allowed to move. So if you were to have positive charges on a conductor, you know that like similar charges don't like to be next to each other, right? They repel. So what ends up happening is that all the positive charges kind of like congregate towards the edge, because they're trying to get as far away from each other as they can. And the way they do that, right, is to move out towards the edge. So now, if I were to, for instance, draw a Gaussian surface in the center here and look to say, hey, how much Q enclosed is there? That equals 0, right? There's no charge enclosed here because all my charge has moved out towards the edges. And in that case, right, I would have the electric field being equal to 0. So yeah, this is why electric field is 0 inside conductors. However, right, if you were to look at the electric field outside the conductor, let's say like right here, let's say like we draw our Gaussian surface here, okay? Now, Q enclosed is positive, right? Because you are enclosing all these charges. So in this case, E would be, greater than 0, or just like not equal to 0. Or you can say positive, whatever, you get it. If there are negative charges, E would be negative. So the electric field inside would be 0, and then as you got outside, you would start to enclose. You would you would be enclosing all that charge that was on the edge. So now you do have an electric field. And kind of cool thing here, if you wanted to draw a graph of this, let's say a graph of the electric field as a function of the position. Let's say this is E as a function of X. Or let's say R. Okay. And this measures R. Okay. And then let's say that this distance out to here, you know, is R, but to the edge, that's like R is equal to like A. Or let me use a different color than light blue. Use orange. How should we intuitively think about this? Like, from pattern recognition, I can tell, but I'm still a bit unclear about the fundamental reasonings. Yeah, so the reasonings here is that electric field from Gauss's law is dependent on the charge enclosed inside the region. What's up, Aleph? And so conductors don't want charges chilling in the center. They want to be as far apart from each other as they can. And the only way for them to get as far apart from each other as they can is to move out towards the edges. We're doing a little bit more Gauss's law, Aleph. So, for instance, if all the charges are on the edge, if I want to measure what the electric field is as R gets bigger and bigger, right, up towards A, that electric field is going to be 0. Okay. So here, from R is equal to 0 to A, the electric field is 0. And then once you get to the edge, like once you get right here at R is equal to A, now suddenly you are enclosing charge. And if we remember, right, E times 4 pi R squared is equal to Q enclosed over epsilon naught. So in insulators, the charge is distributed throughout the whole thing. And I'm going to do an example of that. Well, yeah, charge is stuck, exactly. Amelia says, I would think that for positive charges to be as far away as they can from each other, they'd randomly distribute. No, because then they're close to each other. Think about it. This charge, since it's at the edge, only has to deal with this one and this one. If it was in the middle, right, then it has to deal with like all these other charges around it. Yeah. Think about it. It's like the charger's like, ew, you got cooties, right? Everyone just like runs out to the edge being like, no. I want to get as far away as I can from everyone else, and that's on the edge. You're right that, I mean, they are going to still be somewhat interacting with each other, but on the edge, they're only interacting like with, you know, a couple charges next to them. Anyways, so this, right? This is EA. The inner shell is negatively charged. Inner shell is not negatively charged. Where do we say negatively charged? If you're talking about a different question, I'll get to that. I think you're talking about like a neutral shell, and then there's a positive charge inside, and then like you have to look. We'll do that, but we haven't dealt with any negative charges here so far. Okay, so from this, right? Exactly. Yeah, yes, Sophia. The charge enclosed is the same, but what I'm going to show you here, right, is that the 4 pi r squared changes, right? So remember, if we're looking out here, so this is like, for instance, R is greater than A. This would be like R is equal to A. So there's no charge enclosed as radius goes from 0 to A. Once you get to A, now suddenly your charge enclosed is big, right? And so you would have a big jump here in your electric field, okay? And so, right, from this equation, you get that E is equal to 1 over 4 pi epsilon naught, right? Q enclosed over R squared. This is the same thing, right, as K Q over R squared, which you should recognize, right? That's the same thing as the electric field for just a point charge. But as I get further and further away from the surface here, right, this R goes up, but I don't enclose any more charge. So what ends up happening is your electric field will now drop as 1 over R squared. And so this is a very important thing. We do this all the time in physics to draw diagrams of like how the electric field varies as a function of the radius. So important, right? For a conductor, the electric field is 0 inside, so there's no electric field until you get to the edge. Now suddenly you're enclosing charge at some distance R, and that distance R is now equal to A, because that's the edge. And then as you get further away, R goes up, but the Q enclosed does not. You're not enclosing more charge as you start looking further and further out, but your R is increasing, so your electric field is dropping by 1 over R squared. Okay. I'll give people like a second to ask some questions about that. And then we're going to go over the... Yeah. Conductors have no electric field because any of the charge congregates on the walls. Because charge does not want to chill in the middle. Charge feels safe when it's away from other charge, and the only way to get away from other charge is to go towards the wall. It's like, that's the safest place. Yeah. Yeah, if they were in the center, they would feel forces and they would move. They're exactly. For insulators, charge cannot move. Exactly. So here, this is the electric field for a conductor. So here, let me organize this a little bit, sorry. So this is Gauss's law. Sorry, let me fix this. This is an insulator. This is a conductor. And this is electric field. We say for like a conducting sphere. We haven't done solid angle. It does. So the charge is enclosed once you get outside of the sphere. Once where you're trying to measure electric field, which is where you're building your like imaginary Gaussian surface, is outside of the sphere. Now you do see enclosed charge. But when you are inside the sphere, there are no charges there. The charges are all on the boundary. They're all on the edge. So if you're not enclosing any charge in the little imaginary surface you're creating, then there is no electric field on that imaginary surface. That Gaussian surface is what we call it. Because all the charge is on the edge. So once we get to the edge, or like right past the edge, now we're suddenly enclosing charge, and that's why the electric field spikes and jumps up. Yeah, let's do. Yeah, let me do the electric field for an insulator. Okay. So insulator, charges uniformly distributed. Here, charge is only on edge. Or they say like the surface of it. Okay. But let's do an insulator. Let's say like finding. Exactly. Perfect, Fidekai. You got it. Nice. Good job. Okay, so finding E for an insulating. Or an insulating sphere. Whatever. And let's say of charge Q total. Okay. Let's say it has some total charge big Q. Okay. So when I draw my insulator, which let's say it's just like wood. Wood's a great insulator. Okay. And let's say it has some charge Q total such that the charge is frozen, right? The charge does not move to the edges. The charge is uniformly distributed. Copper is a conductor. Yeah, we don't want it to be copper. This is an insulator. Okay. All right. Okay. So in this case, right? And then, yeah, let's create some definitions for like what distances are, right? Let's say that this is A. We'll get to a SIB. I'll show you. Okay, so let's consider a Gaussian surface, right? That is at some location here, right? Some distance R. Okay. Let's write out our equation, right? So E times, so here we're going to do, for R is less than A. So I'm going to say E is equal to 4 pi, sorry, E times 4 pi R squared, right? Is equal to Q enclosed over epsilon naught, all right? Now here's the key thing, right? As I start walking R out, oh, maybe he's grounding himself. Fedekai. Maybe that's what he's doing. Unless he's just like trying to kill himself. So, as we start walking R out, we're going to start enclosing more and more charge. Okay, so we need to come up with a relationship for Q enclosed based on how far out I am from the center. And here's what we can say, right? Is that, okay, well, Q enclosed must be equal to the percentage of the total volume times the total charge, right? So for instance, if you are taking up 100% of the volume, then your Q enclosed is 100% of the total charge, Q tot, okay? The way they also kind of write this is, oh man, do they use rho or fuck? I don't remember like which variable they use. Sigma, rho. Nah, sigma surface. Volume charge density. Oh, it is rho. Okay, cool. It is rho. All right, never mind. Yes, it is dealing with charge density. Yeah, okay. So here's what we want to say is that the amount of charge you enclose is proportional to the amount of volume that you're enclosing. So in reality, right? So like Q enclosed is equal to the rho here. This is called like the volume charge density times V enclosed. So this is like the volume enclosed, okay? In the same way, right? You know, density is equal to mass over volume, right? You remember like mass is then equal to density times volume. We can say that charge, which is like mass, is equal to charge density, volume charge density, times the volume that you're enclosing. So volume charge density, that's equal to Q total divided by 4/3 pi A cubed, right? This is the volume of a sphere. And then the volume you are enclosing is 4/3 pi R cubed, right? The other way to look at this, right, is like if I just like put these two things together, this is the same thing as like Q enclosed is equal to 4/3 pi R cubed over 4/3 pi A cubed times Q total. And this looks like, right, the percentage of volume enclosed. Because 4/3 pi R cubed, right, that's the volume of this imaginary Gaussian surface, and then 4/3 pi A cubed, well, that's the total volume of the sphere. Yeah. So this is cool. Because you should see some things like kind of cancel here, right? Like the 4/3 cancel. Pi's cancel, yeah, whatever, right? And so what you end up getting is that Q enclosed is equal to R cubed over A cubed Q tot. Okay? That's the amount of charge you're enclosing as you're going from 0 to the boundary, okay? So, if I'm now taking Q enclosed, and here, let's dump it into this. So now all of this is going to go into here. You end up getting E times 4 pi r squared is equal to r cubed over a cubed Q total over epsilon naught. Let's move the 4 pi r squared over. So you get E is equal to r cubed over a cubed. Well, let me leave it this way. 4 pi r squared a cubed. Oh, there's an epsilon naught there as well. Then this is Q total. It is. We assume it is. We're going to do a clicker question where it's not. And then you got to use calculus.
Oh, no.
I don't know. It was just in the clicker questions. Okay, but here's the cool thing, right? Okay, watch. R's cancel. So you're left with just 1, right, on the top. Let's get rid of that. And so you end up getting that E is equal to 1 over 4 pi epsilon naught, which this is the same thing as K, right? And then this is times R Q tote. Okay, so this is equal to K Q tote times R. All over A cubed. Yeah. Cool. Yeah, change in materials. Yeah, maybe something's like fluffier in the inside, but it's like more dense on the outside. I don't know. Stuff varies. So the cool thing you should see here, right? A is a constant. That's just how big the sphere is in total. So we see that electric field is linear, right? As we get up to A. And then again, once you're outside, once R is greater than A cubed, or R is greater than A, sorry. Now you're no longer enclosing any more charge. So now you just have E times 4 pi r squared is equal to Q tote over epsilon naught. And this just gets you E is equal to K Q over r squared. Okay? Because as you move outside of the sphere, right, you're not enclosing any more charge. So the charge enclosed is just Q tote. You don't have Q enclosed being a function of R. So this is kind of cool. If you were to draw, again, like the graph of this. Let's say we drew electric field versus R. And then, right, from 0 to A, you would then see a linear line, right? Okay. Let me see. What do we call A? Yeah, we'll do it pink. Whatever. Fine. Or green. Yeah, we'll do it green. Yeah. So from 0 to A, the electric field goes up linearly as R, right? You see how, like, as R gets bigger, electric field's going to get bigger? Okay. But then once you are outside, then it drops off again as 1 over R squared. So you end up seeing this. Kind of cool. Nice little... I forget what they call this. There's a name for this in the music industry when you have like this type of pattern. I think it's called like a surf wave, maybe? It makes like cool sounds if you have like a linear line and then an exponential drop. It's how Skrillex gets those like whoop 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 noises. But yeah, that's the electric field as a function of R for a non-conducting insulator that is uniformly distributed. A is the radius of the circle, or radius of the sphere. Radius of sphere. Yeah, this pattern is really cool. Like a linear attack and then like an exponential decay. It does a lot of cool things with like LFOs. So, yeah. Cool. Now, of course, this can get all sorts of wacky, complicated when we start doing like shells inside of shells. I don't know if I have time to go over that today, because I want to get us through the clicker questions, which look pretty tough. But yeah, what you can end up doing sometimes, just as like a little preview, is they'll make things like this. It's a little preview. They'll do like shells inside of shells, and they'll put like different charges on different things, and then they'll ask you to figure out like what the electric field is everywhere. And so you have to do like case here, case here, case here, case here, and then case here. And you have to think about, oh, am I enclosing more charge as I go out? Oh, is the amount of charge the same because the electric field is 0 here, if it's a conductor? So yeah, this is what they end up doing later. And it's also how like it's how like coax cable works. Anyone know what coax is? So let me find. It's not as bad as it looks. Yeah, it's annoying, is what it is. Yes, used in the PC. Yeah, here we go. So this is, for instance, what like, yeah, here, let's, this is kind of cool. Yeah, there you go. So this is, if you ever like get cable or something, if you do science, you end up dealing with a lot of coax cable as well. But coax cable has a lot of different things, right? So like, for instance, this is an insulator, right? You have braided shields, which are conductors. You then have a dielectric, which has magnetic properties, and this is an insulator. And then you have a center conductor. This usually carries your signal. So this is usually like your shield or your ground, and then this is your positive for the signal. And if you were to like slice that down, it looks like this, right? And you can calculate what the electric field is everywhere from like the center all the way out to here. What you end up finding, right, is that the electric field here, if this is a conductor, right, it's 0 until it gets out to here. And then here it drops off as 1 over r squared. But then here, it stays constant because, or the electric field is 0. But you end up having like positive, here's what kind of happens. If this is like positive, right? And let's say that this thing is neutral. Let's say this has positive charge. Let's say like Qn is net positive. And then like that Q out is equal to 0. In order for this to be neutral, what you end up having is you have like negative charges here. And you have positive charges here. But together they sum up to like be 0. And so the charge you enclose ends up being 0 here. It's pretty cool, right? You have negative charges on this wall, positive charges on this wall. The Q you enclose is 0. But once you get outside, now you're enclosing both positive, negative, positive, and it's a net positive. Yes. It looks like the telecom cables you can illegally cut for copper money. Don't do that. Don't do that. Anyways, I think we're going to get into this more when we do potential. Because it's kind of boring with the electric field being 0. But when we start talking about potential's cool. Because then, like, the potential's constant here or something. Is copper that expensive? I don't know. I mean, everything's expensive these days. Eggs are not $3 anymore. I think I paid like 7 the other day. What, for eggs? Yeah. Okay. Let's see some clicker questions. Because I think these have like non-linear densities that depend on like R. So there's only one question today, but it's 3 parts. Okay, but here we go. 2 kilometers can get you a lot of egg money. Yeah. Okay. And let's get the answer choices for this one. So if you want to follow along and just solve this. I love everyone's describing like monetary hustles to like steal cable. Don't get the FBI on my stream, please. Okay. A ball of radius r carries a positive charge whose volume density depends only on the distance r from the ball center as follows, where rho naught is a constant. So this is actually pretty cool. So if you look at this, right? Rho is equal to rho naught 1 minus r over r. So as the radius gets out to be the actual radius of the circle, this goes away, right? You get 1 minus 1 is 0. And so this is a case of where it has like decreasing charge density as you get further and further out. Yeah, if you were to graph this, it would probably look something like this. Okay. So, they say, first of all, find the magnitude of the electric field as a function of the distance outside the ball. Ooh, that's cool. I like that. Outside's easy, right? So, if we are outside of the ball, okay, now we can say, okay, E 4 pi r squared is equal to Q enclosed over epsilon naught. And we got to think about, okay, outside is the amount of charge I'm enclosing changing. Thanks for the following tour. And it's not. Yeah, I know. Mass density and charge density are the same symbol. Yeah, it just depends which thing you're working with. In general, right, this is like linear density. This is area density, and then this is volume density. Those are just the 3 terms we use. So outside, I'm not enclosing any more charge, so this is just going to be equal to Q tote. Okay, so I need to figure out Q tote, right? So Q total is going to be the integral, and this is going to be like a volume integral, right? We're going to say like dV, right? Volume integral of the volume charge density, right? If I integrate the charge density times the volume, then I'll get the total charge. If this was not dependent on R, or like not dependent on like how much volume I'm getting out, right? Q tote would just be equal to rho times like 4/3 pi r cubed. That would be nice, but it's not. I can't just say like, you know, volume times charge density and get Q, because the volume charge density is changing as we move throughout the sphere. So I have to integrate this. Okay, so in that case, I'm doing a volume integral. What method should we use? I think I want to use spherical shells. So I think what I'm going to do is I'm going to build like a spherical shell, and I'm just gonna like increase those like further and further out. I think that's what I want to do. So here, I'm gonna integrate from 0 to the outside radius, which is big R, okay? And what we're gonna do is we're gonna do the surface area of a shell. Yes. No, when we did surface area, it was this. This is, I think, which kind of looks like path integral, I guess, right? I think they do this and they say like SA. I think here we're going to do this and say like volume. I think that's the technically correct thing to do. But okay. So the volume integral is going to be going from 0 to R, and that's going to be 4 pi r squared, right? Times dr. So this is like the dv part, right? Oh, you are right, Fedekai. Yeah, you are right. And then the volume, I think, is 3. Yeah, he's talking about this. I think this right here is like surface area. and then the 3 is volume. Yeah, you're probably right. All right, let's be consistent. You know, I'm cool with that. Let's do it. Like that. Yeah, okay, good. All right. So this is dV. So this is like my changing volume, right? It's like the surface area of a sphere times like how much the surface area, how much the sphere like expands. All good. So that's the dV, right? And then rho in this case was rho naught, and it was 1 minus I think it was r over little r, right? Little r over big R. Okay, cool. Exactly, Sib. Yeah, we're taking like the surface area of a shell and then like multiplying it by the thickness of that shell, which is dr. I think this should work. Let's pull some constants out. I can pull these things out, right? So I can say like, okay, cool, 4 pi rho naught. And then I have 2 different integrals, right? I have this, well, here, let me just write it out. So 0 to r, and then we have 1 minus r over big R, just dr. So that's going to be 4 pi rho naught, and then there's 2 separate integrals here, right? So we have 0 to r of dr minus the integral of 1 over big R, r dr from 0 to r. So I separated this as one integral, and then I did this as like another integral. I'm doing this on the fly with you guys. I actually don't know if I'm correct, but we'll see. So this is just going to be r, right? And then it's just r from 0 to r, okay? And then this is going to be minus 1 over r, and that's going to be r squared over 2 from 0 to r. I did forget the r squared. Thank you. Uh-oh. Thank you, Catberry. Yes, I totally forgot the r squared. Oopsies. Okay. Yeah, I was like, this is getting like too easy. Yeah, no, okay. So this is r to the 3rd. All right, we got to fix this. Good. Thank you for calling it out. Okay, so this is r to the 3rd over 3 from 0 to r minus 1 over r to the 4th over 4 from 0 to r. It applies to both. Yes, thank you as well. That's a good... Yep, that's laziness on my part. No, this isn't Stokes' theorem. So volume is definitely a triple integral. Technically, I should be integrating r dr d theta. Sorry, d theta d phi. But I'm making a simplification of I'm doing the 0 to 2 pi in terms of theta, and then the negative pi over 2 to pi over 2 in phi, and then I'm just having the integral of dr. That's where this comes from. This comes from like the d theta d phi. I think there's like a sine theta in there too. Yeah, it's one second. I'll find it for you guys. Where is it? Yeah, okay, this is technically it. It applies to both. Yeah. So yeah, technically, if you wanted to do the full triple integral, you would need to do it's r squared, and this is different for it's sine phi, and then it's dr d theta d phi, but we end up getting just 4 pi r squared if we know it that we're just integrating a sphere. The simplification is nice, yeah. Okay. Let's see if we get the right answer. Let me see real quick. Okay. So this is 4 pi rho naught, right? This is going to be big R to the 3 over 3 minus, so that's going to be big R to the 4th over big R, so that's just going to be R to the 3. So that's going to be R to the 3 over 4 Okay. Common denominator here is 12. Right? So we're going to have 4 pi rho naught. So this 4 and 4, right? That's going to be 4 over 12 r cubed minus 3 over 12 r cubed. And so you just get 4 pi rho 0 over 12 r cubed. Because 4 12s minus 3 12s are 1 12. Exactly, because, yeah, you're totally right. Okay, cool. So this is Q enclosed. I know, that took a little bit, it's a little bit of calculus. Okay, and, right, we had E times 4 pi r squared was equal to Q enclosed over epsilon naught. So I'm going to have E is equal to 1 over 4 pi r squared. And now this is going to be 4 pi rho 0 over 12 r cubed. All this is going to cancel. Goodbye. This cancels with this. And I'm left with rho 0 r cubed over r squared over 12r squared. And there's an epsilon naught in there, sorry, as well. Yeah. Okay. Is that any of the answer choices? Let's see, which answer choice is that? That looks like A, right? R cubed rho naught over 12 epsilon naught r squared. Yeah? Okay, cool. I think the answer choice is A. After we did all that. So let's go for part A here. Select answer choice A. Check answer. Correct. Okay, cool. Alright, now let's go to part B. Sorry, this music is really loud. Let me turn it down. Actually, I wasn't supposed to have any music the whole time. Sorry, were you guys cool with the music? I forgot I had the lo-fi still running the whole time. I'm just so used to it at this point. Alright, let's... All good? Cool. Alright, where is my stuff? This. It's fire. See, I didn't even notice. Yeah, right? Maybe I should start putting, like, I don't know, speed runs of, like, Minecraft or something at the bottom of my thing. You know? I think I filtered it out. Yeah, it's like white noise. Okay, here we go. Okay, find the magnitude of the electric field strength as a function of the distance r inside the ball. Ooh. This is gonna be tricky. Yeah, Subway Surfers, right? Let's just do some Subway Surfers. Okay, so now I'm inside. Now I'm on the outside. Okay, this is going to be R, right? And again, let's remember this whole thing is big R. It's all about just finding Q enclosed. It's really all it is. So E 4 pi r squared is equal to Q enclosed over epsilon naught. So Q enclosed for R is less than R. Let's figure that out. Q enclosed is going to equal to integral from 0 to little r, right? We're not going all the way out to big R, right? We're going out to location little r, where I'm measuring the electric field. And it's still going to be rho dV. Okay, cool. So I think we can borrow some inspiration from here, because we already did that, right? The only thing that changes is the bounds, right? Okay, so let's just get to the point where we do the bounds. So you do the same derivative, or same integral, sorry. This is the only thing that changes. So instead of integrating from 0 all the way out to the outside, I'm integrating to r. Okay? So let's take our result from here. As, you know, just save ourselves some time. I don't really want to redo all the integrals. Okay, so here's the key thing. Is we are no longer enclosing all of the charge. We're only enclosing the charge out to location R. So like dot 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 from before. So now, yep, here's the change. Now only enclosing part of the sphere. Okay. So that's going to get me 4 pi rho 0. And now this is going to be r to the third over 3 minus 1 over big R, r to the 4 over 4. Interesting. Oh, wait. Let me put what the answer choices are for this so we can see if we're kind of getting along the same result. Oh, what? Actually, oh, no, I don't want all this again. My bad. Part of the sphere. You know what's funny, actually? So YouTube is actually cracking down on that. Just a little tangent here. Yeah, just for any of you guys that are creators, YouTube is gonna start demonetizing any video that has just bullshit AI in it. So I'm pretty sure you've seen these, right? These lazy YouTube videos where they just rehash things and put an AI voice over it. They're gonna start demonetizing all of them. Yeah. So it's kind of interesting. Yeah. So I wonder if that'll affect the Subway Surfers. You're not allowed to just rehash content. Okay. Money hack. Infinite money glitch. I am teaching, yeah. It should be fine. Yeah. Okay, so here, this is Q enclosed. Cool. So then we can go from here. My side hustle. Yo, tuition's not cheap, man. You gotta do what you gotta do. Okay. Just start digging them wires, dude. Now we can't be committing well, I guess that's vandalization is what it is, but okay. 4 pi's cancel, 4 pi's cancel. E is equal to 1 over epsilon naught. And now that's gonna be rho naught over r squared. And then we have r to the third over 3 minus 1 over big R, r to the fourth over 4. There's a really big one in the Atlantic. I think you might be violating some international treaties, though, if you start, digging that one. You're going to have a couple countries mad at you. Yeah, take it back. All right, this is going to cancel out this, and then that's going to make this r squared. So now we have r over 3 minus 1/4 r squared over big R. I feel like I pull out another r there, couldn't I? Okay, let's see what answer choices we had. What answer choice do we have to deal with here? Because we always got to make it look kind of like what we got. So let's see. I don't see any 2 pi's. There should be no 2 pi's here, right? Actually, there shouldn't be anything with pi in it. So I can instantly just say, this is not this. This is not it. Okay. I do see some, 3's Again, no 2s. There's no 2s in our answer. So that doesn't work. That doesn't work. Oh, they pulled out a 3. Okay. So you could pull the 3 out, and then you got to put a 3 up here is what you got to do. Okay. I see how this works. This is the same thing as rho naught over epsilon naught. Yeah. They don't pull any R's out, though. They pull out a 3, which, I don't know, that's kind of weird. Weird flex, but okay, whatever. So if you pull out a 3, then this becomes R. I was thinking about, like, what happens when I multiply it back. I should get the same thing. So then this is 1 minus 3 over 4. R squared over big R. Which is the... oh, that's this one. Okay. Cool. Answer choice should be E. It's kind of a weird... It's a weird, weird way to do it. But whatever. You gotta, like, make sure it looks the same. Kudu's so extra, yeah, dude, what? Kudu do be extra, bro. Nice, we got it right.
Good job.
Oh, man. Do I gotta take a fucking derivative here? Dude, excuse me, what? Here's part C. I don't know if I'm gonna be happy about this. But okay, let's see. So it says, find the point R max at which the electric field is maximum, and then also find the electric field there. Okay, so let's take our results from both of these. So, yeah, you have mostly constants. You are right. So, okay, let's remember. For R is between 0 and big R, we had E was equal to rho naught over 3 epsilon naught. And then it was R minus 3/4 R squared over big R. I think that was it, right? Okay, cool. And then the other one we had was just rho naught R. Okay. And then for R is greater than big R, we had E was equal to rho naught epsilon naught 1/12 or 12 epsilon naught, and then big R cubed over R squared. So let's see, is this continuous? I feel like it should be, right? No. Yeah, the exam, I don't have anything like... Hey, what's up, Zach? I don't have any... Yeah, nothing on the exam is super intensive like this with calculus. Maybe on the final, but I would let you know. I mean, this is cool. You should be able to do this. Because you are definitely going to have to do this when you take upper division. Like, they're going to make you do all derivatives and integrals. Okay, so where's this max? Da, 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 da. I feel like I want these to have the same thing on it. So I'm gonna make this like I'm gonna make this a 4. I'm gonna make this a 12. I just multiplied by 4 over 4. And then I'm gonna pull the 4 in. Because it makes it easier for me to, I think, see things. Because now I have rho naught over 12 epsilon naught. And now that's 4 little r minus 3 r squared over big R. Okay, because here's the cool thing, right? So when R equals big R, right? Then I get 4R minus 3R. Wait, shouldn't there be an R cubed in there, though? Right. This would become 1. And then this would become 1. Okay, so it's continuous. Yeah, so what I was checking is that, like, if R equals big R, do these two electric fields equal each other? And they should, right? We would hope it's not, like, discontinuous. Unless it's the case of the conductor. Then you do get discontinuous because suddenly you just see charge out of nowhere. Okay. Where is it maximal? So that's where dE dt is equal to 0, right? So if this is a calculus thing, right? Anytime you want to maximize a function, you want dE d whatever. In this case, is dE dr is equal to 0. So that can't really happen here, right? Because the only way for the derivative of this would end up being like negative, and then it's 1 over r cubed, and you're never going to get 0 from r in the denominator unless you go out to infinity, which is like not really possible. So I think it's this one. So let's do dE dr for 0 less than r less than big R. So that's going to equal to rho naught over 12 epsilon naught, and then that's going to be 4, right? Derivative of 4r dr is just 4. And then that's going to be minus 6r over big R. Okay, cool. So now I see where this derivative is equal to 0, right? It's where this is equal to 0. So I need 6r over big R to equal to 4. So I need r to equal 4 big R over 6, which equals 2/3 big R. Cool. Where did the second E equation come from? This? Oh, so all I did is I took my original equation, which I think was this over 3, right? This was the original thing we got. And then I multiplied it by 4 over 4. And the reason why I did that is because now these things have like the same thing out front, and I'm just comparing this to this. And then I brought the 4 in. And that's how you get this. This came, we did this earlier, right? This was done here. That's when we figured out what the electric field was outside of the sphere. That was our final result. Yeah. So this right here is outside. And this right here is inside. Okay. Yeah, I was just checking to see if it was continuous. Well, also because I didn't know if the electric field was maximal somewhere outside, right? What I instantly figured out here is that, like, if I do dE dr here, right? So in this case, right, if we were to do dE dr, I end up getting rho over 12 epsilon naught r cubed, and then that becomes times -2 1 over r to the 3. And this is impossible for dE dr to equal 0 unless r goes to infinity, which is nonsensical. I don't really care about that. And obviously, I mean, that's the minimum, right? Because once you get really, really far out, your electric field should drop out to 0. So I know it has to be somewhere inside. I figured out that was at 2/3 R. Okay, so where is that? So let's get some answer choices. So it's not this one. It's not this one. Okay. Choice A or choice C. I think the next thing to do is just to plug this in. So just take, so this is equal to R max. So then E is equal to rho naught over 12 epsilon naught, and that's going to be 4 times 2/3 big R minus 3, and then that's going to be 4/9 big R squared over R. It's kind of ugly. Okay. Rho naught over epsilon naught. That's going to be 8/3 R minus 12/9. So that's 4/3. 4/3 r. So that's going to be rho naught over epsilon naught. And that's going to be 4/3 r. Oh, there's still a 12. Almost forgot the 12. My bad. Okay. And then 4 over 12. This is 1 over 3. So rho naught over epsilon naught. And then that's going to be big R over 9. Wow. Which is choice A. Nice. Okay. Cool. So, oh, I hit my footpad. Okay. Sorry. There we go. So, yeah, answer choice there is going to be A. Let's go back to Kudu here. I think answer choice is A. Check answer. Correct. Nice. All right, we did it. All right, cool. Went a little bit over, but nice. Okay, so that's Gauss's law. We're done. Test is tomorrow. I will put out an announcement on Campus Wire later. I gotta edit the test this afternoon per Albert's suggestions, but I will be available via email, and so will Albert. Ask Albert first if you have questions about the test. I have to do some. I have some meetings on campus I have to go to about my job. So, but Albert should be available for sure if you have any questions about the exam. You don't put it on Campus Wire because that's technically cheating. So, I mean, before the exam is released, you're allowed to ask whatever. But while the exam is out, try not to use Campus Wire to ask about the exam because that's like really obvious. Yeah, and it will open at 12:30. Yes, you're welcome, Nemo. Glad you found it interesting. Yeah, this is physics. Okay, cool. All right. Enjoy the rest of your Thursday. Enjoy the weekend. I will open a chapter probably Saturday or Sunday, but that pre-lecture won't be due till like Tuesday. So, yeah. All right, good luck on the test, everybody. Any questions, hit me up on Campus Wire, and I will see you guys on Monday. No lecture on Friday. Just do the exam. Cool. All right. Peace out.